Alright, let's continue with looking today at the exact distribution of the sample population. Alright, remember your sampling proportion, p hat. So let's say you have 20 bulls, 5 of them are red. And that is your population. Okay, so keeping that in mind, the population proportion of red bulls is going to be 1/4. So your p-value, which is your expected value of the x variable, let's say of the red bulls, is going to be 0.25. What we do with p hat, which is a sample, it will have a specific size, and you would choose a sample and you would determine the sample proportion. But that usually what you do is you don't know anything about the population when you start with. That's the whole point of sampling. You take smaller samples of the same size and you're going to do some calculations to extrapolate to the whole population. So here we choose a sample of size 5 and we pick a sample, and from that sample its proportion is 1/5. So this is just experimental. Okay, and so on. This is another example and you get a different proportion. Okay, before I move on, that proportion, as you take different samples, is in itself a random variable. We will look at its distribution, and for any distribution there's things that we need to know: the expected value and the standard deviation, to see where it's centered and how it spreads. We're gonna look, when we look at the sample proportion, we're gonna look at two situations depending on the population size. Is it a small population or a large population? Okay, so let's look at a small population and we're gonna do some sampling. We're gonna get some calculate the sample proportion, we're going to do a distribution, and finally we're going to get the expected value and determine the standard deviation. Our small population here is a bag of balls. You have 6 blue and 4 red. That is your population, and we're going to focus on the number of blue balls. So the population proportion, which is fixed, it's 6/10 or 3/5 or 0.6. Once you take a sample of a specific size, you can calculate the probability of having a certain number of blue balls and red balls using the knowledge of selections or combinations. Okay, so when you have a combination n x, it follows this formula. Okay, so x will be the number of objects, and n is how many you can how many choices do you have. Hang on, do I do this right? Is the number to select? Alright, so x is how many you selecting, and n is from how many objects. Yep. Okay. So let's look at an example with a calculation. You have, again, it's the same. We look at this situation. Is it the same? 6 and red? Yep. Okay. So it's the same. Now we take a random sample. It's a size 4. What is the probability that there is one blue ball in the sample, or the proportion of blue ball is 1/4? So 1 is blue ball, 1 is the number of blue balls, and 4 is the total number, is the sample size. Okay, the way you do it is, first you need to find all the number of ways you can have with 4 balls. So you select 4 balls out of 10, that's your combination, you get 210. That will form your denominator. Here at the bottom, this is how you determine your probability. Then you must have 1 blue ball, okay? Knowing that is 6 blue balls in the bag, it's going to be 1 blue ball out of 6, so that gives you 6 ways, which goes down here on the one of the factors of the numerator. And as you have 1 blue ball, the other 3 balls have to be red. So it's 3 red balls out of 4 red balls, because we have 4 there. So your combination 4 3 gives you 4 different ways, which is 4 3 here. So you write your ratios of selections, and that gives you your probability after you simplify it. So that gives you the probability of having 1 blue ball, and the other 3 have to be red. So what we just answered, hang on, what was the answer? It's 4/35. Wait, why do I have a different probability? Yes, it's the same, sorry. That's 24/210, and it's simplified, but we're gonna go back to 210 because all the different probability or proportion will be a fraction out of 210. So when you have, we just solved this one. So 1 blue ball is a proportion of 1/4, and that gives you your probability. And you can do that for 0, 2, 3, and 4. Notice the 4, the last one, is the proportion of 4/4, which is 100% or 1. You get your last row, which is the respective probabilities. With what you're going to be interested in for your sampling distribution table is you're going to have the first row is going to be your proportion. So we're going to ignore the number of balls because that's your x variable or your p variable. Oh, hang on. Let's say it's your x variable. It's the number of blue balls. But what we're interested is into a proportion. So it's the number of blue balls divided by the sample size, and that gives you a proportion. So it always starts at 0, always finish at 1, and then it's a fraction out of the sample size. In the middle, it's 2/4, which is simplified to 1/2. By focusing on a table that has p hat as the first row, the second one is your probability. So we have a probability distribution for the random variable p hat, and that is called a sampling distribution, and that's what we're after. And from that sampling distribution, we can answer questions related to probability, and later on we're going to look at calculating looking at the center, so the expected value and how it spreads with its standard deviation. Alright, let's continue with the previous example. So we have the same situation. Now you need to use the sampling distribution, that's the previous table, and you want to find the probability that the proportion of blue balls in a sample of size 4, so it's the same as before, is more than 1/4. So here is the sampling distribution. Our probability is sampling proportion has to be greater than 1/4. So greater than 1/4 is probability of p hat is 1/2, 3/4, and 1. So we get the sum over 3. We write down the respective 3 probabilities, simplify, and we get the final answer. So that's how you calculate your probabilities. If you now, instead of having a large a small population, remember, for a small population you can use your knowledge of selections. When we move to a larger population, what's happening is when you select a sample that is from a large population is too large, then what we need to do is we assume that the probability of observing the attribute we are interested in is constant for each selection. What it means is we're gonna go back to a binomial distribution. So what is constant? That p-value of 0.7 is for the whole population. In that example, is 70% of all 17 years old in Australia attend school, and that attribute is constant. Okay, that's coming back to the binomial distribution. Now, when you do your sampling, you have a size 4. Your probability that you get a certain number of students attending school will go from 0 to 4, 4 being your sample size, and you're going to use your binomial formula to determine the probability. So that's your p, that's your 1 minus p, and in front that's your combination of 4 and x. From that, what you can do is you start with your variable, so it's the number at school in that sample, so 0 to 4. You translate that into a proportion. You calculate your probabilities using the binomial formula. We concentrate on the last two rows and we get our sampling distribution. So for that example, it relates to that same situation. We're looking at the probability that the proportion attending school is less than 50%. So less than 0.5, that implies from you look at your sampling distribution, it's 0 and 0.25. You extract the respective probability and you calculate it. A little bit of notation. So for population, it's mu, sigma, and n, capital N. When you look at your sample, it's your x with a bar on top, it's your mean. For the standard deviation is lowercase s, and the sample size is lowercase n. So anything Greek is for the and also italic. Just keep that in mind when you see that in printed text. Alright, so here again from the previous example we have our sampling distribution. I just want to review how to calculate the expected value of that sampling proportion, as well as the standard deviation. We're gonna going back to a what we did in the discrete random variable. So this is discrete. For the expected value of p hat is the sum of the products. So you do the products vertically. So here are the products, and for all of them you just add them at the end, and that gives you 0.7. Notice how that 0.7 is actually the same as your population, and that's going to be useful later on. But that's the way you would calculate it for a discrete random variable in general, which is what you have in that sampling proportion as well. For the standard deviation, remember the variance is your, before the square root, your variance is the expected value of the variable squared minus the square of the expected value of the variable. Our variable here is p hat. The expected value of p hat squared, what you do is you multiply the probability with the expected value and you square the expected values. So do that on the calculator, you get that amount, you substitute in here, and we get that standard deviation. Okay, now to simplify that, Remember how I said the expected value of that sampling proportion was very alike. It was actually the same as the expected value of the whole population. Um, if we go back to so the expected value of p hat is going to be p. That's through that proofing. Okay, so that's confirming what we did in the example before. How do we get there is p hat is defined as the x is your number of favorable outcomes, so it's the number of students attending school, and you divide by the sample size. That is a linear combination of a random variable. By doing some manipulation here, we ended up with equal to p. We can do the same with the standard deviation. It's a bit of a language here. Okay, yeah, it's the for a sample, the expected value of that sample is also called the unbiased estimator. So it's an estimator. That's the another technical term. From the example, that's the application. You just substitute the values. Wait, ignore that one. Hang on. All right. For the variance, a little bit of working out here, but it's very similar to what we have for a previously. So our standard deviation is you're going to use that formula. P is your probability of success. So it's very similar to the binomial, except you divide by the sample size. This is also called the standard error. It's annotated SD of p hat. We haven't done that. Let's skip that. Okay, so in summary, when the population is small, the sampling distribution proportion you can determine by using our knowledge of selections, something you need to review and being really familiar with. If it's a large population, then you're going to use the knowledge of the population, which would be its as a binomial random variable, and you will know p and also the population's your n value, and you can respectively calculate the expected value and the standard deviation of p hat, which is your sampling proportion. Alright, and that's it for 17b, and I'll see you in the next video.